Hi, my name is Rajesh Chitanvis, and my project is design and simulation of parallel HEV with speed and torque coupling. What is a parallel HEV? Parallel hybrid systems have both an internal combustion engine and an electric motor that can both individually drive the car or both coupled up jointly, giving the power together. The output shaft of engine and motor are coupled together using a speed coupling or a torque coupling, and the power is transmitted to the final drive and to the wheels. The electric motor gets its power from battery, and engine gets its power from the fuel tank. The examples of parallel HEV are Toyota Prius, a Chevy Malibu, Honda Insight. Okay, I have compared these three cars here. So the price is almost same for all the three, just $2,000 difference. Fuel economy is higher for Toyota Prius, which is 58 miles per gallon in city and 53 miles per gallon on highway. The CO2 emission is lowest for Prius, which is 132 grams per kg, and the size of these cars are Toyota Prius and Honda Insight are a mid-size hatchback, and Chevy Malibu is a mid-size sedan. Okay, so the project goals to build a parallel HEV with a better fuel economy than Toyota Prius, which will also have a low CO2 emission than Toyota Prius. Obviously, the manufacturing cost should be lower than Prius. We'll try for that, and we'll use torque and speed coupling to couple the engine power and the motor power. Simulation. So this is the graphical view of Toyota Prius power drive on Autonomie. The power drive name is HEV Power Split Midsize Gasoline Powertrain, which is similar to the Toyota Prius powertrain. Parts which I have used in simulation: the chassis is of Toyota Prius, the planetary gearbox is of Toyota Prius, transmission and final drive is of Toyota Prius. The engine is of the latest Toyota Prius, which is 71 kilowatts. The motor one, I modified this. I'm using the Toyota Camry's hybrid motor here with 88 kilowatt power. The motor 2, which is used for which is used as a generator to generate electricity while regenerative braking, is of Toyota Prius. And batteries, which Toyota uses nickel batteries, I'm using the lithium-ion batteries here. So this is the simplified view of all the parameters of Toyota, our powertrain. So by clicking on driver, we can go in driver and change its parameter. So by clicking on each of these, we can go inside and change its parameter. So if I want to change the engine parameter, I'll click on engine and change its parameters. So I have kept these parameters for my powertrain. The driver parameter is, I put driver weight as 80 kilograms. In battery parameter, I have changed the SOC initial, the SOC max and SOC min of the battery. In engine, I have changed the Prius engine power to 71 kilowatts. So whenever you put your power here, the mass of the engine is adjusted according to your power. So the mass gets adjusted. The same way, when you put the motor power, the mass of the motor is being adjusted here. It is auto adjusted. Motor 2 parameters. So motor 2 is the normal Prius motor, and it has the 53 kilowatt power. Torque coupling parameters. The torque coupling ratio of Prius is 0.486, which I got from Toyota documents. Chassis parameters. So as we are using the Toyota Prius chassis, we'll be putting the parameters accordingly. So the aerodynamics drag is 0.24, the frontal area is 2.2 meter per square, and the total body weight of chassis is 840 kilograms. Final drive parameters. Final drive ratio is 3.26, which I got from Toyota official website. For the wheel, we put the Toyota Prius wheel radius, which is 0.3175 meters, and the rolling resistance coefficient over here in first row. Then we select the two cycles. The HWFET cycle is for highway, and UDDS cycle is a city cycle. So we'll run our vehicle on highway cycle and a city cycle and see what we get outputs. So next we go in the run process. In run process, we perform the simulation. Before performing, we make sure that all the parameters are inserted and the cycles have been selected, both cycles. Results. Okay, so these are the results. As you can see, our fuel economy of our modified powertrain is 84 miles per gallon on highway and 48 miles per gallon in city. The fuel economy is better than Prius. The CO2 emission is 104.6 on highway, which is much less than Prius CO2 emission. Okay, so the estimated total manufacturing cost for our vehicle will be around $17,000, which is not too bad. These are the engine torque and speed graphs, and as you can see, when the simulation 3, the blue one, is for the highway, and simulation 4 is for the city. So as you can see, before the speed goes up, the torque goes up, and when the torque is lowered, the speed increases. So you can see that for both in city. Compare these two green graphs. Here the torque go first and the speed is low, and then the torque falls down and speed increases gradually. These are the motor torque and speed coupling graphs. So again, here you can see when the torque increases, the speed decreases, and when the speed increases here, the blue line, the speed is high, the torque is 0 or closer to 0. Same with the simulation 4, which is the UDDS cycle. When the speed increases, the torque is almost 0 or near to 0, and when torque increases here, the speed goes down. This is the engine efficiency graph from Autonomie report. So the conclusion can be, after changing the motor of Prius to 88 kilowatt Camry motor and the primary nickel batteries to lithium ion batteries, we get better performance, we get better fuel economy, which is 84.56 miles per gallon on highway and 48.94 miles per gallon in city. The CO2 emission is less than Toyota Prius initial, which is almost 120, and we got 104. Manufacturing cost is also affordable. It will be around $17,000, $18,000. So these are my references. That's it. Thank you.